The transformer architecture behind large language models is built around one main goal. Given a sequence of words, predict what comes next. It's essentially a neural network that takes a few input words and produces the next best fit. If you want to learn more about how that works, I'll leave a link for you that explains neural networks. Transformers are essentially neural networks with a few enhancements that actually make the difference, and they're what produced the ChatGPTs and Claudes of the world. In this video, we'll discuss such enhancements. Before any word is put through the system, it's converted into a set of numbers called embeddings. Why? Because numbers are much easier to work with. Then, these embeddings are modified in two key ways. One adds information about where each word appears in the sentence, and the other helps the model understand context between words. In this video, we'll focus on that first part, how transformers learn position using something called positional encoding. We'll talk about context in future videos. When a sequence of words is fed into a transformer, the first thing it does, after converting each word into its embedding vector, is give the model a way to know where each word is in the sentence. An embedding is simply a list of numbers that represent a word's meaning in mathematical form. For example, the word far might be represented by a vector like 0.49, negative 0.74, 0.28, etc. Each number captures a small piece of meaning, maybe tone, context, or relationship to other words. But these embeddings are static. The same word always starts with the same set of numbers, no matter where it appears. That's a problem because the model can't tell if far is the first word, the fifth, or the 10th. To fix that, we add another set of numbers, one for each position in the sentence. These are called positional encodings. They inject information about order into the embedding, so the model knows not just what a word means, but also where it is. Importantly, these positional values vary both from word to word and from dimension to dimension. If every word got the same positional numbers, the model couldn't tell positions apart. So, each position, first, second, third, and so on, has its own pattern. And if every dimension followed the same pattern, you'd just get scaled copies of the same information, which wouldn't help. So we need the change in every dimension and every position to be different. In the original transformer, this is done using sine and cosine waves of different wavelengths. Here's how it looks mathematically. For even dimensions, 0, 2, 4, etc., we use sine. And for odd dimensions, 1, 3, 5, etc., we use cosine. The variable POS is the word's position in the sequence, and I is the dimension number. The denominator 10,000 to the 2i over 10, where 10 is the dimension of the embeddings, controls how fast each wave oscillates, smaller for early dimensions, larger for later ones. This means lower dimensions capture broad position trends, like whether a word is near the start or end of the sentence, while higher dimensions capture fine-grained differences, like the distance between the fifth and sixth words. Together, all these sine and cosine patterns create a unique positional fingerprint for every word in every dimension. No two words share exactly the same combination, even across long sequences. Now, why do we use both sine and cosine? Because together they form a 2D rotational representation of position. If we only used sine, positions like 0 and 2 pi would both have a sine value of 0, so they'd look identical. By adding cosine, which is 90 degrees out of phase with sine, each position gets a unique sine-cosine pair. For example, for position 0, we have sine equals 0, cosine equals 1. For position pi over 2, sine equals 1, cosine equals 0. For position pi, sine equals 0, cosine equals negative 1. And for position 2 pi, sine equals 0, cosine equals 1. This circular pairing ensures that every position can be represented as a point on a circle, with both direction and distance encoded. Using both also makes math between positions simple. When the model compares two positions, say I and j, it can use a trigonomic identity, sine I cosine j minus cosine I sine j equals sine I minus j. That's huge. It lets the model compute relative distance directly from the encodings without any extra training. And since attention in transformers is based on dot products, these sine-cosine pairs make it easy for the model to measure how far apart words are in the sequence. With sine alone, the dot product wouldn't capture the full phase. Half the positional information would be lost. So, sine and cosine aren't just arbitrary choices. They're the perfect mathematical way to encode both position and distance smoothly across all dimensions. Now, theoretically, we could assign completely unique numbers to every position and dimension. And yes, that would make positions totally distinct. But that approach wouldn't generalize. It would only work for the sequences the model has seen before. Sinusoidal encodings, on the other hand, are smooth, compact, and continuous. They scale to any sequence length, even ones never seen during training. So, while more unique sounds better, in practice, structured patterns beat random uniqueness.